Assalamualaikum and hi everyone. In this video, we will discuss topic 4, which is about the magnetism. I will divide into two parts. The first part is subtopic 4.1 to 4.3 and the second part 4.4 to 4.6. First subtopic is about the magnetic field. Magnetic field is defined as a region around a magnet where a magnetic force can be experienced. It is also can produce from the motion of electric charge or changing of the electric field. Magnetic field has two poles, the north pole and south pole. Like pole will repel each other and opposite pole will attract each other. There are few sources of magnetic field, and the figure will show the lines of the magnetic field produced from each sources. First, take a look at the bar magnet. For a bar magnet, you can see that at the north pole, the magnetic field leaves the north pole and enter the south pole. If you have two magnet bars, for the opposite poles, it will attract each other, and for the like poles, it will repel each other, produce a neutral point at the center. The second source of magnetic field is current-carrying conductor. There are three types of current-carrying conductor, which is straight wire, circular coil, and solenoid. When the current flow in each conductor, it will produce the magnetic field around it as shown in the diagram here. The third source of magnetic field is from the Earth magnetic field. Earth magnetic field is like a giant bar magnet. This is because the north geographical pole of the Earth is actually near the south pole of the Earth magnetic field, and the south geographical pole of the Earth is near to the north pole of the Earth magnetic field. And here are the symbols to show the direction of the magnetic field. We will use the dot symbol to show the direction of magnetic field out of page, and cross to show the symbol for the direction of magnetic field into the page. Here are characteristics of magnetic field line. The first one is the lines do not intersect one another. The lines form a closed loop. The lines leave the north pole and enter the south pole, and the lines are close together at the poles. Second subtopic is about the resultant magnetic field produced by current-carrying conductor. Figure shows the current-carrying conductor in a straight wire. We can use a symbol to show the direction of the current from the top view. For example, if the current moving upward in the conductor, we can use the symbol of dot circle, and if the current moving downward, we can use the symbol of cross circle. For the magnetic field produced by the current-carrying conductor, we will use the right-hand grip rule to show the direction of magnetic field or to identify the direction of magnetic field. If we have a straight wire, our thumb will represent the direction of current, and our four fingers is represent the magnetic field direction as shown. If we have current-carrying conductor for a solenoid, our thumb represents the magnetic field direction or north pole, and our four fingers represent the direction of current. The example shows the direction of magnetic field when the current flow in a straight wire. From the top view, we use the symbol of dot circle to represent the direction of current moving upward, and the counterclockwise circle represent the direction of magnetic field around the wire. For the side view, at the right side of the wire, we can represent cross symbol for the direction of magnetic field directed into the page, and at the left side, we use dot symbol for the direction of magnetic field out of page. If we have two straight wires carries current in the opposite direction as shown, from the top view diagram, the dot circle symbol represents the current flowing upward with the direction of magnetic field counterclockwise, and the cross circle symbol represents the current flowing downward with the direction of magnetic field clockwise. We also can sketch the magnetic field direction at a point, either at the point A, B, or C, using magnetic field arrow, if we want to calculate the resultant magnetic field at that point. To calculate the magnitude of magnetic field for the current carrying conductor, first, for a long straight wire, B is equal to mu naught I over 2 pi r, where r is the distance from a point to the wire. At the center of the circular coil, B is equal to mu naught I over 2 r, where r is referred to the radius of the coil. At the center of solenoid, B is equal to mu naught Ni, and at the end of the solenoid, B is equal to mu naught Ni over 2, where the N is the number of turns per unit length. Mu naught is permeability constant, which is equal to 4 pi times 10 power of -7 Henry per meter, and I represent the current flow in the conductor. For subtopic 4.3, which is about the force on a moving charged particle in the uniform magnetic field. The charged particle that is moving with a velocity v in a uniform magnetic field B will experience a magnetic force. The magnitude of magnetic force is given by the equation of QV cross B or QVB sin theta, where theta is the angle between V and B. For the direction of magnetic force, we will use the Fleming-Hens rule. Referring to the Fleming-Hens rule, the thumb is represent the direction of magnetic force, the index finger represent the direction of magnetic field, and the middle finger represent the direction of velocity. Fleming left-hand rule can be used to identify the direction of magnetic force for the positive charge that moving in the uniform magnetic field, and Fleming right-hand rule is for the negative charge. Here are the examples to determine the direction of magnetic force on a charged particle. If we have negative charge moving with the velocity v perpendicular to the magnetic field B, so we can use a Fleming right-hand rule to identify the direction of magnetic force Fb. From the Fleming right-hand rule, the direction of magnetic force Fb is to the left. If we have the positive charge moving with the velocity v perpendicular to magnetic field B, to identify the direction of magnetic force exerted on the positive charge, we can use the Fleming left-hand rule. And from the Fleming's left-hand rule, we can identify the direction of magnetic force exerted on the positive charge is to the right. A charge moving perpendicular to a uniform magnetic field will experience a magnetic force, which acts as the centripetal force, causing the charge to move in a circular path. Referring to the figure, if we have positive charge moving with the velocity v perpendicular to magnetic field B, Fb exerted on the positive charge cause the positive charge to move in a circular path as shown. We will get the relationship between the magnetic force and the centripetal force, which is Fb is equal to Fc and R is equal to mv over qb. Thank you for watching and learning with me. And thank you for subscribe my channel Cikgu Nun. I wish you all the best. Thank you.